Hello everyone, my name is Aidar, and in this video exercise 7 we will talk about validation of climate forcing data. In hydrological modeling, accurate and reliable input data is crucial. Before we dive into model calibration and simulations, we need to ensure our input data is accurate and complete. Poor data quality can lead to misleading results, affecting the reliability of your model predictions. Checking your input data helps avoid errors and ensures your model's outputs are trustworthy. As you can see in this visualization, input data plays foundational role in the modeling. Therefore, we need to ensure that input data are in good quality. After that, we can proceed with the model setup, calibration, validation. If all these steps are well prepared and well done, then we have a good model. Common types of input data in hydrology include meteorological data like precipitation and temperature, hydrological data such as stream flow and groundwater levels, and land use data. But in our case study of the Rashan River Basin, we have only precipitation and temperature data. And here are key steps in input data checking. First of all, we need to ensure that all required data points are present. For example, here are the graphs with the example data that has no missing data at the bottom, and at the top one has some missing data points. And this missing data can lead to gaps in the analysis, affecting the accuracy of the model. There are different reasons for missing data points to occur. First of all, equipment malfunction or failure. Sensors, instruments, or data logging equipment can fail, leading to missing data or incorrectly measured data. Second, human error. Mistakes in data entry, recording, or transcription can result in incorrect or missing data. Third, inconsistent data collection or data loss or corruption. It can be caused by software bugs, hardware issues, or data transfer errors. This can occur during storage, transmission, or processing of data. Fifth reason, some restricted access or privacy concerns. For example, some data is present but is not available by different reasons, or some country or institutions have their strict data sharing policies. Sixth reason, inadequate measurement resolution. Instruments with low sensitivity or inadequate resolution may fail to capture certain data points. Seventh reason, environmental factors such as weather, ice phenomena, environmental disasters. Ninth reason can be changes in data collection methods, switching between different measurement instruments, techniques, or data collection standards can create gaps if the transition is not seamless. And sometimes data points are intentionally left out if they are deemed irrelevant, sensitive, or anomalous without proper explanation or documentation. And understanding the reasons behind missing data is crucial for addressing them appropriately and ensuring the quality and reliability of your dataset. Next, you need to check the data consistency. Verify that data collected from different sources or periods is consistent. Inconsistencies can arise from changes in measurement techniques or data entry errors. Next, we do the accuracy verification. Compare data against known standards or benchmarks. If available, you can use some different dataset with a similar characteristics to verify the accuracy of your input data. Also, it's important to check for outliers. Look for data points that are significantly different from the rest. Outliers can indicate errors or rare events and need to be carefully evaluated. Ensure all data is in the correct format and units. Inconsistent units can lead to calculation errors and misinterpretations. Use tools like GIS software, data visualization, and statistical analysis to identify issues. Automated scripts can help in checking large dataset efficiently. For example, in this study case, we use the R programming for data visualization and statistical analysis to find the problems with our input data. And these challenges like data gaps, inconsistent sources, and maybe outdated data are very common. Address these problems by using interpolation methods, cross-referencing multiple data sources, and updating datasets regularly. In conclusion, input data checks are vital step in the modeling process. They ensure that the data you use is accurate, complete, and reliable, leading to more accurate model predictions and better decision making. Always allocate time for thorough data check before starting any modeling because it is an investment in the accuracy and reliability of your results. And be careful because small mistakes in the beginning can accumulate and become much bigger in the end of the project. In the following example, I will show you how the data quality check may look like. And in this example, we will check the precipitation data. So let's start with the script. You can safely run without any changes first two parts where we have libraries and functions. So these parts we shouldn't change anything there, and you can click run all chunks above. After it finished, we may proceed to the data and parameters. The data and parameters should be the same as you had previously. We have river name, basin name, code name, and directory to the discharge monthly data. Then we need to load the same data but the decadal one. Next we specify the path to the GIS folder and we load the watershed, DEM, everything the similar to what we did previously in previous videos. Then we do the parameters for climate extraction, which also is the same from last one, where you only need to adjust the directories and maybe the years of your study and the model directory. Then you may adjust the directory for figgrep variable, which is the directory to store the figures if you want them to be saved. Next, you need to adjust the HRU shapefile name. In this case, we use the HRU without glaciers UTM, and then it uses the JS path, and this HRU should be saved in the GIS path. Run it, then there is a new part of the script which processes the HRU file, and then we can plot it. Now we can have the visuals of HRU, and if you want to save it, you can run this part of the script, but I already saved that, so I don't need to run it. Here we load the CHELSA data, which we already did in previous videos, so we can just process the temperature and precipitation data again. After the processing is done, next we do the validation of precipitation with observed lapse rate data. And given the problematic forcing in the Zeroshan River Basin, we have a new section of code here for validation of the precipitation data with the lapse rates. This is done by comparing the precipitation data for each elevation band with observed precipitation lapse rates that are obtained from the Soviet Compendium on Water Resources of the Soviet Union on Amudarya and Sirdarya rivers. And in the first chunk we compute total norm precipitation for each elevation band separately in millimeters per year, and we then compute the basin average by multiplying each elevation band value in the column elevation band area, and then we summing the result and dividing it by the total area. After that we have the precipitation norm value here. Then let's plot the elevation gradient of the precipitation for each elevation band, and here it is. Next we do the same plot, but instead of elevation bands we have the elevation in meters. Then we plot the measured lapse rates, and here is the scatter plot of the Soviet era data of the Ravshan River Basin norm precipitation rates, and these precipitation and these data were available in a book from Ivanov from 1971, Resources of Surface Water, Central Asia, and these data were digitized using the plotdigitizer.com. And then these lapse rates were used to rescale the precipitation data of CHELSA. Next we have a comparison of CHELSA data with the measured lapse rates. Here is in black CHELSA precipitation lapse rate and measured during the Soviet Union the lapse rate. Measured lapse rate from the 1971 in blue. The CHELSA lapse rate is derived from satellite data and represents the latest available information. In contrast, the measured lapse rate is based on historical observation from the Soviet Union time. And how to decide which lapse rate to believe as the true precipitation values in the Ravshan River Basin? We don't have exact answer to that. We need to consider all advantages and disadvantages of both measurements and both lapse rates. So what are advantages of CHELSA precipitation lapse rate? So first of all, it's up to date and utilizes the latest satellite technology to provide this data, and it has wide coverage, offering comprehensive special coverage including areas where ground measurements may be sparse or unavailable. And there are also disadvantages: potential overestimation, as seen in this figure, and uncertainty in calibration. Satellites data may require complex calibration and validation processes, which can introduce some uncertainties, especially in the remote areas where the ground measurements are not available. And the measured historical lapse rate, they have their own advantages. It's a historical benchmark. It provides a reliable baseline based on actual historical measurements and accuracy. Ground-based observations are more accurate and representative. But in this case we have certain disadvantages. These lapse rates are outdated. This data is from 1971 and may not reflect current climatic conditions. And given these two lapse rates, in this case we decided to rescale it to measured lapse rate from 1971, and this rescaling is necessary for several reasons. Firstly, we would have improved accuracy. By aligning the CHELSA data with historical observations, we can correct for overestimation and achieve more accurate precipitation estimates, and we would have more consistency because rescaling ensures consistency with the long-term historical data, making it easier to compare past and present conditions, and reliable model inputs. But again, I want to remind you that each case study is unique and in different conditions, in different region, in different area, in different time. We might ignore observed lapse rates, but in this case, we'll rescale it to the measured lapse rate. And as we can see, the measured lapse rates, they don't have the range that is provided by CHELSA precipitation lapse rates. That's why we need to interpolate in the next chunk of code the measured lapse rate, and then we need to compute the scaling factor. And here in this graph we can see the scaling factor for precipitation of CHELSA, and in the next chunk we here need to decide whether to rescale the data or not. If you don't want to rescale your data, then you can just put N, that stands for no, or if you want to rescale it, you need to press to type Y, that stands to yes. Run it, and then you will have the rescaled historic observation precipitation data here. Next chunk of the code is similar to what we had in the previous videos, where we combined all the data and add discharge to have the files ready for RS Minerv. Here we have added the if we have a rescaled one, then use the rescaled file. And the following chunks of code will be similar to what we already had in previous videos. So for additional validation, you can run the chapter 7, the cross-check forcing data downscaling results, and see everything, all your data in the plots for several elevation bands. For example, here we can see the graphs for different forcing data that we have. You can change the number here for elevation band, and for example, if you want to look closely to elevation band number 10, you can write it the number 10 here and run the script to see, and you can see the visualization for your input data for elevation band number 10. Thank you for your attention. If you have any questions, you can ask us via email or write your question in the comments. See you in the next videos. Bye.